Two-column proofs. A proof is a logical argument that shows a statement is true. One method for writing a proof is a two-column proof. This may be the hardest part that you have to deal with in geometry, because what you're going to be doing is identifying things that you know are true about certain shapes, and you can see it. You can see that these things are true. Like in your mind, you know this is absolutely right. But what we need to do is get on paper in some format. We're going to use the two-column format. You got to get it on paper in some format, and that's really hard. It's one thing to be able to see it and to get that that would make sense, but it's a totally different thing to be able to, put it in words, or in this case, put it in some structure that we call a two-column proof. All right, now before we start any of the proof writing here, we do need to tackle some properties that I have here. I've got the reflexive property, I've got the symmetric property, and the transitive property. Up at the top it says, the following properties are true for numbers and shapes. What we're mostly going to be applying this to will be shapes. Now the shapes that you're going to see these related to will be segments and angles. And for each of the properties, we're going to be looking at the segments and the angles in terms of equality and also in terms of congruence. Equality is going to refer to using the equal sign. Congruence is going to refer to when you're using the congruent symbol. Reflexive property. All right, once I start to fill things in here, you're going to think that this is completely silly, that there would be no reason to ever use this property. Okay, but I promise you, you're going to use this one a lot. It just seems a little bit odd at first. Basically, what the reflexive property tells you is that something is equal or congruent to itself. Okay, let's consider a segment. Suppose that we have a segment called AB. Okay, AB, that would be line segment AB, is congruent to line segment AB. It's congruent to itself. Right, sounds really silly, but surprisingly, you will use this a lot when you're writing proofs. All right, as an equality statement, we can basically have the same thing there, but just with an equal sign. However, when you do that, you're gonna need to drop off these bars here, and what you would say is that AB is equal to AB. Again, something equal to itself. But in this case, because we're talking about equalities, this is really the distance from A to B is equal to the distance from A to B. Sounds silly, you're gonna use it. Okay, angles. For angles, we could say that angle A is congruent to angle A. It's congruent to itself. And we can say that the measure of angle A is equal to the measure of angle A. All right, symmetric property. This one, you're not going to use it a lot, but you are going to use it on occasion. Really, if you're strategic about how you write your proofs, there's a good chance that you don't need to use the symmetric property. But there are going to be a few occasions that it's going to pop up and you'll want to use it. Symmetric property really allows us to take the left side of an equal or congruent statement and switch it with the right side of that equation or congruent statement. Okay, let's look at the congruence again first. For segments, we may have the statement, let's write it this way. If, I want to squeeze that word in there. If line segment AB is congruent to line segment CD. You've got line segment AB is congruent to line segment CD. If that is true, then line segment CD is congruent to line segment AB. Okay, what we're allowed to do is flip the sides on here. Okay, again, that might sort of seem like an odd thing that you'd want to do, but depending on how you write the proofs, it could be important that you have things on the right side. If you're very strategic, you might have it already set the way that you want, but if you don't have it set that way, then you can just use the symmetric property to flip them around. Okay, for the equality, pretty much like what we saw in the reflexive part, if AB is equal to CD, the distance from A to B is equal to the distance from C to D, then CD is equal to AB. The distance from C to D is equal to the distance from A to B. For the angles, if angle A is congruent to angle B, then angle B is congruent to angle A. For the equality, if the measure of angle A is equal to the measure of angle B, then the measure of angle B is equal to the measure of angle A. And last, the transitive property. This you're going to use a lot. You're going to be using the transitive property a lot. What it sort of does is it connects two ideas together using a third piece that you're later able to drop out. Okay, you're going to notice that this looks a lot like something that we've seen before. And I hope as we do it, you'll remember what that thing was called. Like you'll recognize that we've done it and it was called something else. It's just in what we're working on right now, it will be referred to as the transitive property. All right, so for segments and congruence, what this would say, it's a little bit of a long one. If line segment AB is congruent to line segment CD and, whoops, not that letter, and line segment CD is congruent to line segment EF, then line segment AB is congruent to line segment EF. Okay, so AB is equal to CD, well, it's congruent to. AB is congruent to CD, they're the same. CD is also congruent to EF. So if we were to take out, call it a middleman here, take out the CD, we could just make the statement that AB is equal to EF. Okay, logically, that's how that would work. If these are the same and these are the same, then all three are the same. So AB can be congruent to EF. The quality part is the same thing that we see here, but with just different notation. Okay, so if AB is equal to CD and CD is equal to EF, then AB is equal to EF. Okay, so now we're just talking about the distances between the points, but it follows that one pretty much the same. All right, and last for angles and the congruence, if angle A is congruent to angle B and angle B is congruent to angle C, then angle A is congruent to angle C. All right, and for the measurement, if the measure of angle A is equal to the measure of angle B and the measure of angle B is equal to the measure of angle C, then the measure of angle A is equal to the measure of angle C. All right, so now that we got all those properties somewhat squared away, at least we know that they exist and they could be used for something coming up. What we're gonna do is get into the main thing that we've been building up to in the past few videos here, which is how to write a two-column proof. Notice that this is a two-column proof because you've got two columns that go with it. All right, for a two-column proof, you're gonna be asked to prove something. You're usually going to be provided some information as well. Sometimes you'll be given a little bit of hints, little facts about whatever it is that we're doing that you're going to need to eventually get to your concluding part, which is the proof portion of this. Okay, so in this, you're provided with this information that the measure of angle 1 is equal to the measure of angle 3. Now you're going to notice that that already has markings in the pictures. So sometimes the given information is actually just provided in the image for you. All right, and now what we need to do is prove that the measure of angle EBA, that angle there, so that's actually angle 2 and 3 together, EBA, prove that that angle measure is equal to the measure of angle CBD, which is here. So that'd be 1 and 2 together. Okay, we want to prove that EBA is the same thing as CBD. Now, most of these proofs, what they kind of begin with is making an observation about just in general what you see there. And I think in this case, you can see enough information when you keep outlining those angles, you can see enough information that tells you that those two angles have to be the same size. Okay, so let's go ahead and just address what you've probably already noticed here. EBA is angle 2 and 3 together. That's what it is. CBD is angle 1 and 2 together. So both of the angles that we're identifying here have a portion of them which is angle 2. The parts that are different between the two angles is this part here, which we're calling angle 3, and this part here, which we're calling angle 1. But look, part of the given information was that they're the same size, right? So EBA is made out of angle 2 and an angle that's equivalent to 1. CBD is made out of angle 2 and angle 1. So I think we can at least tell here logically that they need to be the same size. That, yeah, that makes sense. So the real challenge is, the new stuff for us is, how do we actually write that up? Not just point to things and say, well, if these are the same, then this all should make sense. But actually structure it in a logical way that's going to get to this final conclusion. All right, so in our two-column proofs, the two columns that we have, one is called the statements, the other one is called the reasons. The statements is all the stuff that we're actually doing, all the things that we're going to do with the angles to eventually get to what we want to prove. The reasons, you're going to notice that there'll be one per one. They're going to correspond. So every decision that we make, everything that we write down as we go through the statements is going to match up to something that is in the reasons. All right, statement number 1, you can see that it is missing here, right? We don't have anything for that spot. Most of the areas I actually do have filled in for you here, because this is a brand new concept, and what I want to make sure we do is not try and design everything from scratch in your very first example, but give you an idea what the structure is, and then start to get a concept of how the statements and the reasons actually go together. Okay, so we're missing the first statement, right? There's nothing there. But the reason that goes with it, it says given. Okay, so that's information that you don't actually need to produce on your own. It's actually provided for you, and the given information was up here. It's that the measure of angle 1 is equal to the measure of angle 3. So we're going to begin with that. Most proofs you will begin with the given statements, but a little bit later on you'll start to figure out that using given statements maybe in different locations throughout the proof is a little bit more fluid in the structure of how it would read. Okay, so this one does start at the beginning. We start with that fact: the measure of angle 1 is equal to the measure of angle 3. All right, and then we're gonna kind of leave that behind for just a bit here, and we're gonna work on something different. So we're setting that up because we're gonna need it a little bit later on. All right, next, the measure of EBA. All right, remember that was one of the angles that we want to show to be equal to the other. Okay, so EBA over here, that is equal to the measure of angle 2 plus the measure of angle 3. Something that visually we were able to see. Right now what we're doing is writing an equation to show that. All right, now recall that if you add two angles that are adjacent together to get the larger angle, that is referred to as the angle addition postulate. Okay, so they're all the things that we do. Everything that we do, we acknowledge in the pictures and we're going to apply it. There's going to be a reason that goes with them. Some of them have very specific titles that go with them too, like angle addition postulate. All right, now, the next part here says the measure of EBA, the same one that we're talking about, is equal to the measure of angle 2 plus the measure of angle 1. Well, that's not actually apparent in the picture there, right? EBA is actually 2 and 3 together. But previously, we mentioned from the given statement that the measure of angle 1 was the same as the measure of angle 3. So what we're able to do is swap out the measure of angle 3 with the measure of angle 1 because it was mentioned previously. So there's this organization that we need to create when we write the proofs. State some things a little bit earlier that you want to use later on. Now, when angle 1 goes in for angle 3, we're going to call that the substitution property of equality. Okay, so now we got that equation. All right, next, number 4, the measure of angle 1 plus the measure of angle 2 is equal to something. Well, obviously it's going to be equal to EBA, but we've already made that statement, so there's no real reason to go there. What we want to say is that the measure of angle 1 plus the measure of angle 2 in the picture over here is actually the measure of angle CBD. That's equal to the measure of angle CBD. And that is the angle addition postulate. I guess once you see the reasoning that goes with it, it might remind you what we did in line 2, okay? All right, but now here's the really neat thing. We only got one more spot left. We only got one more thing left according to how I've outlined this here. The very last part always has to be what you're trying to get to. So we're gonna end up writing that the measure of angle EBA is equal to the measure of CBD. That always has to be your last line, because that's what you're aiming to get to, is that proof. All right, now how do we get there? We're going to use the transitive property. Okay, remember the transitive property. We just looked at that. The transitive property over here, we want to look at the angles part. It says, and I think we're talking in terms of measure. Yep, so we're going to look over here. If the measure of angle A is equal to the measure of angle B, and the measure of angle B is equal to the measure of angle C, we can take out B, and we can just say that the measure of angle A is equal to the measure of angle C. In our case, the overlapping information is going to be this piece here and this piece, the 1 plus 2, measure of angle 2 plus measure of angle 1. Those are the same. So if it's equal to EBA and it's also equal to CBD, we can use the transitive property to just say that these two angles are equal, and that gets us to our conclusion. All right, for our second proof, we have a picture of a segment AC with a point B sitting on top of it. All right, our given information is that AC is equal to AB plus AB. That's interesting. AC, the whole thing, is going to be equal to the length of AB plus itself AB. So what does that tell us about B? That tells us that B is going to be a midpoint. It's a midpoint of the whole thing, right? Because if the length of that doubled would become the whole thing, then it means it's the same length as that side, and B is a midpoint. Okay, so there's some things we can discover on our own. What we need to prove is that AB is equal to BC, that AB is equal to BC, which sort of goes with, yeah, if B is a midpoint, then these two would be the same. All right, but now how do we structure it with our statements? We'll go ahead and start with our given. AC is equal to AB plus AB. All right, and then we're going to write this. AB plus BC is equal to AC. So let's take a look at what that is. AB plus BC is equal to AC. Sounds logical, right? Well, that one also has a name. That is the segment addition postulate. That is the segment addition postulate. We just previously used the angle addition postulate. All right, so we now have that. Let's see here. AB plus AB is equal to AB plus BC. Okay, so there's a lot to look at there, but you might recall some of these from the previous lines. AB plus AB is right here. AB plus BC is right there, right, from the two different lines. But check this out. These two together, AB and AB is equal to AC, and AB and BC is equal to AC. So we're sort of taking out the middleman, the one that would connect these two together, and that is the transitive property. That is the transitive property. Okay, so now we can say that these are equal to each other, and moving from here to our last line, which is what we need to get to, we had AB, AB, we had AB, BC. We're now down just to an AB equals BC. We actually lost an AB on each of the two sides. We lost an AB on each of those two sides. Now recall that when we talk about AB without the line on it, we're talking about a number value, the distance from A to B. So all these are worth certain values. They're worth numbers. And that's also why you can have the plus and the equal signs between them. Okay, so how do we go from here to there? We subtract AB. That's what we do. You can also refer to that as the subtraction property of equality. But specifically what we did is we subtracted AB from each of the sides.
Wait, what?